Hello, welcome to this 8-minute supplement on Galileo for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. In the 4th century BC, Aristotle taught that an object falls in proportion to its weight. A stone twice as heavy as another falls twice as fast. For many centuries, this was accepted as true. It seemed reasonable and logical. But in the 1600s, Galileo thought about this, conducted experiments, and concluded that differing weight does not affect how objects fall when we can ignore the effect of air resisting the motion, and even with air resistance, they do not fall in proportion to their weight. Likely you have heard that Galileo proved that heavy and light metal balls fall at the same rate by dropping both off the Leaning Tower of Pisa, and they hit the ground at almost the same time. In his Discourses Concerning Two New Sciences, written during his final years of home confinement imposed by the Vatican, Galileo has his protagonists say that upon dropping a 100-pound cannonball and a 1-pound musket ball, they hit the ground at almost the same time. But historians doubt that this particular experiment ever occurred. Shortly we will examine an experiment from Galileo, but first there is an interesting thought experiment attributed to Galileo. I don't know whether this is factual or not, but it's useful to think about. Imagine a heavy cannonball and a light musket ball connected by a thin and light but very strong wire. We drop the connected balls from the Leaning Tower of Pisa. What will happen? Let's start with the assumption that by themselves, unconnected, the heavy cannonball would fall much faster than the light musket ball, as Aristotle taught. Then, when connected, surely the faster falling cannonball will pull the slower falling musket ball and speed it along faster than it would fall by itself. That seems obvious. But maybe the slower falling musket ball retards the faster falling cannonball, slower than it would fall by itself. Maybe both of these happen and the coupled balls fall at a speed in between the individual balls. But wait a minute, the coupled balls weigh more than the individual balls. Shouldn't the coupled balls fall faster than the cannonball falls by itself, if heavier objects fall faster? This is pretty confusing. It seems like we have two reasonable conflicting predictions from our assumption that by themselves the heavy cannonball would fall much faster than the light musket ball. What if instead we assume that by themselves the heavy cannonball and the light musket ball would fall at the same rate, ignoring air resistance? From that assumption, we can reason that the coupled balls would fall at the same rate as the individual balls. In this case, we get a single prediction, not two conflicting predictions. No contradiction. That seems to make sense. Actually, the two balls would fall at the same rate if there were no air resistance, and they fall at nearly the same rate, falling from a low height with ordinary air resistance. The thought experiment helps us to think about gravitational acceleration. Switching focus, in the absence of air resistance, an object falls in constant acceleration, and the distance it has fallen is proportional to the square of the amount of time since it was dropped. We know this thanks to Newtonian mechanics and Newton's calculus. Prior to Newton, Galileo believed this was the case, as had a few natural philosophers before him. But they did not have the tool of calculus and did not express their beliefs as mathematically as Newton did. How might Galileo have verified that distance was proportional to time squared? Galileo described rolling smooth, round, bronze balls down a smooth groove in a gently sloping 20-foot-long ramp instead of dropping balls vertically. Galileo could see the balls start to roll, pick up speed, and increase their speed. But Galileo had no stopwatch, no electronics, no camera, no clock with a second hand. Galileo described timing how long it took to traverse a given distance using a water clock. However, that might just have been a pedagogical device in his book and not his actual experiment. In the book, The 10 Most Beautiful Experiments, author George Johnson relates a theory proposed by Galileo historian Stillman Drake in the 1970s. Galileo's manuscripts showed that he precisely measured the distances the ball had traveled down the ramp at different time ticks. Drake's proposal is that Galileo sang some well-known song, perhaps a church hymn sung his entire life, with constant beats, and marked the instantaneous location of the ball on the ramp at each beat. Then he repeated the experiment multiple times, refining the location of the ball at each beat. Then finally he measured the distances of the marked ticks. He analyzed the differences of the distances and the ratios of the distances and found his time squared result. Since before the time of Ptolemy, Europeans believed that the sun and the planets revolved around the earth. This was evidence of the perfection of the heavens. Just before his death, Polish polymath Copernicus published his theory that Earth and the other planets actually revolve around the sun. Galileo had discovered 3 moons orbiting Jupiter using his telescope, and so he no longer believed that all moving heavenly objects orbit the Earth. He came to believe Copernicus's heliocentric theory. The Catholic Church deemed the heliocentric theory heretical, and Galileo was constrained to home confinement for the rest of his life.